Hi, I'm Sandy Wells, and my talk is going to be about our recent work in Bayesian estimation of diffusivity spectra in prostate diffusion, MRI. So here's the problem we want to address. Given some observations of diffusion MRI decay, we want to predict the corresponding diffusivity spectra, or relative component fractions. But there are some difficulties. While there's a linear model, it's poorly conditioned. Also, the data is noisy, and there's a constraint that the relative fractions be non-negative. This is the forward model. The predicted signal is a sum of exponential decays weighted by the relative fractions. It can be seen as being a type of Laplace transform. Theoretically, we might hope to directly invert this Laplace transform. However, that is not practical. We can use the least squares approach to estimate the relative fractions, though for this problem we have to use non-negative least squares. This is not hard to solve, as it's a convex problem. But there is a problem. The solutions are unstable, and because of that they are hard to interpret. Instead, we prefer to use a Bayes approach. We construct a Gaussian measurement model and use Bayes' rule to obtain a posterior distribution on the relative fractions. These explicitly show the uncertainty level in the prediction. The posterior distribution is a multivariate normal with a non-negativity constraint, which makes it analytically difficult. So instead, we characterize the posterior by using Markov chain Monte Carlo. In particular, we use Gibbs sampling, which is not too hard to apply in this situation. It makes iterative sweeps over the relative fractions, replacing each current value by a sample from its conditional distribution, conditioned on all of the others. The data was echo-planar diffusion-weighted MRI with 3 directions that are analyzed separately. The images were acquired with a 3 Tesla scanner using an endorectal coil. There were 16 evenly spaced B values, and the signals were averaged over regions of interest. The estimated SNR is 600, and our model has 13 compartments. Here are 2 of the images. The left is B0 image, the right is a B3500 image. The normal tissue is outlined in green, and a tumor is outlined in red. Here are the signal decays, the normal tissue in blue and the tumor in orange. These are some of our results. The box plots show the spread in the posterior distribution on the relative fractions. There's a sizable free water diffusion fraction in both tissues, but it's diminished in the tumor. Very slow diffusion components are elevated in the tumor, and given the predicted uncertainty, we can be pretty confident about that. The normal tissue has a hint of 2 peaks at slow and intermediate values, but we can't be too confident about that given the uncertainty in the predictions. If you would like to hear more about this, I invite you to come to the full talk, which is in the signal representations session at 1700 on Thursday in ICC Capitol Hall. Thanks for your attention.